Right, shall I just fire off?
Perfect. No, let me introduce you, and then you can go off. I'm really excited to have Dima join us. She's a professor, associate professor in computer vision at the University of Bristol in the United Kingdom, and has received her PhD from the University of Leeds in the UK. She's also currently an EP-SRC fellow, and her research focuses primarily on automatic understanding of object interactions, actions, activities using both static as well as wearable visual depth sensors. So with that, take it away, Dima.
Thank you very much. I think Kristen is always a very hard act to follow. I'll give it my best shot. Right, so the title of the workshop is very, very relevant to the work that we're attempting to do at Bristol. However, our focus is primarily on object interactions. And that's why the title of my talk is Compositional and Multimodal Perception of Object Interactions. My neighbors have actually decided to do what we call here a Corona party. I don't know if we can hear them, but if you see some music in the background, you'll figure out what's happening. Right, so what do we mean really by compositional and multimodal perception of object interactions? Then I'll start by an example video, and that will set the tone for what we're talking about. So let's just watch this video, and then I hope you can hear the audio as well. Right, so this is an object interaction. We as humans can understand it. We can hear the aspects of it that are relevant to the actual action, and aspects of the audio that are in the background. We can distinguish the goal. We can also figure out things like, what do you think the person is doing next, right? So we also have this general understanding that might not be in the pixels, but is a little bit more than to understand what the person is attempting to do. And we can do that quite long term. So we can figure out that the person is going to cut the rest of the pepper. We can also figure out that mostly all of these are going to end up in the pan, since the pan is now kind of frying. So if we attempt to do that in a compositional way, we can do that in 2 dimensions. One is a spatial dimension, right? So we can say, what does each image contain? There are the hands here, the actors, there are tools, there are active objects, there are inactive objects. And I think this workshop is very much about understanding the relationships between these. And I'm sure people with us would have seen the intro to the workshop on the action genomes. You can also think about decomposing this temporally, right? You can think about this timeline and say, okay, there are all these building blocks that decompose the action. And if you are in this business of splitting a video into segments and deciding a frame that is relevant, assuming everything behind it is relevant, everything before it is irrelevant, I suggest you look at an earlier work of ours in 2017, which we called Trespassing the Boundaries. I'm very much against this concept of there is this binary threshold that makes things relevant or irrelevant to an action temporally. So that's what we call compositional understanding. What do we mean by multimodal understanding? And this is quite an overloaded term, the term modality or multimodal, right? So some people would say multimodal would be audiovisual, and you've seen Kristen's talk and all the notions of audiovisual perception. Some people use the term language as this additional modality. So they would say vision and language is multimodal. There are also the terms multimodal when it comes to different projections of the video itself. So if you project the video into an appearance and into motion, also people call this multimodal. So this is a heavily overloaded term currently in our community. In this talk, I will address the 3 different overloaded terms, asking the question, how can multimodality achieve compositional understanding without those additional labels? So without setting spatial notions or temporal splits. And I hope by the end, I would have shown you some of the work we've done towards this aspect. But before I do that, it's important to have some videos we can rely on that will allow you to do multimodal understanding. They should have audio, they should have language, and they should have motion, etc. And this is like a project we've been working on for several years now called Epic Kitchens. So just in case you're not very familiar, and also if you don't know the latest update, and just tell you a little bit about Epic Kitchens. The notion of it is to collect a large data set in people's homes. So this data set is 100 hours in length. It contains lots of videos, and these are lots of individual actions. And importantly, it's completely unscripted. So people were not given instructions to record this data set. This is a collaboration led by the University of Bristol along with Catania and Toronto. And the idea started as follows. Let's give people cameras and ask them to record everything they've done in their kitchen for 3 days per person. We ask them to start recording before they walk into the kitchen, stop recording as they walk out, and record everything they do from preparing the coffee in the morning to washing the dishes in the evening. People don't do this type of data collection because how on earth would you ground truth this? Like you have this whole unstructured collection of information. We stole an idea that is very common in movie understanding, which is taking subtitles. So after the data was collected, we asked these individuals to talk over the video, telling us what they've done, giving us basically a subtitle of the movie they have captured. And this was done in free-form language, which is published with the data set, but also parsed to understand what we know as actions, start and end times and verb classes and noun classes. And that was published as dense action segments a couple of years ago in what we currently refer to as Epic Kitchens 55, because it was 55 hours of dense action labels. And then still is the largest data set in egocentric vision, so in videos collected from wearable cameras. In addition to all the caveats I've told you about, which is it's labeled with these narrations and it's also multimodal and it's unscripted. After the dataset was released, and thanks to the interest of the community, we started the extension to the dataset. And we went back to some of the individuals who collected data with us and asked them whether they're interested to collect data again. That gave us a niche aspect of the same individual 2 years on. Can we still learn their actions or recognize their actions? But also new individuals. We've also improved the whole pipeline by an interface we call the pause and talk narrator that allows you to pause as you narrate and avoid missing actions, resulting in an improved density of annotations. So we increase the average actions per minute from 13 to 20. That's already very dense if you talk about 13 actions per minute. And increasing it to 20, we're not missing any actions now. And on the 1st of July, we released the Epic Kitchens 100, which from its name is 100 hours now of densely annotated action segments. The data is naturally collected, so it's very long-tailed. The y-axis is log-scaled. And what you see here is what we call the verb classes and the noun classes. These are not the free-form language. These are grouped into minimally overlapping classes. And the shaded area and the solid colors represent the footage that come from the original Epic Kitchens and the extension. We've also introduced these superclasses that allow you to group things like retrieve and leave, etc. So actions beyond the individual classes. On the 1st of July, this was released, Epic Kitchens 100, the data, the annotations, and an archive paper describing the extension. And actually this morning in the Epic workshop, we released the leaderboards for 5 challenges associated with the dataset. So these are action recognition, detection, anticipation. We have a new challenge on unsupervised domain adaptation for recognition, and also multi-instance retrieval. I'm not going to tell you a lot more about the dataset, so you can look at Epic Kitchen's website, but I wanted to tell you the background of the type of data that we will use to answer the question, which is, how can multimodality achieve compositional understanding? And let's start by the first modality, the easiest to start with, and I'll select language to start with. So the question is, how can language achieve compositional understanding? So I told you about the narrations that we've collected with this dataset, and that's where we will start with. So we will take a sentence that had been labeled with this video, like slice pepper finely using knife. We're gonna parse this sentence into the part of speech, right? So we're gonna say there are verbs, there are nouns, there are adjectives. If you've used any of these parsers, you know that they can give you a little bit more than that, right? They can tell you what applies to what, that this is the noun that's applied to this verb. They can tell you the adjective and which verb it applies to, etc. They're not great, actually, these parsers, but I think if you kind of figure your way around them, you can get a decent parser, and that's what we've done for Epic Kitchens. So I'll tell you about two works that have achieved using language for compositional understanding. The first is this work we presented in ICCV last year. What we've done here is we've taken the caption and the video, and we're trying to do multimodal retrieval or cross-modal retrieval, i.e. you can go from the text and retrieve the video that's relevant from a video gallery, or you can start with a video and retrieve the relevant caption from a gallery of captions. In this work, we use this part of speech to give us this compositional understanding, i.e. we're taking the video along with the verb, and we are providing a verb embedding that is a space where the video is embedded close to the verb, and similarly, all other videos that are related to the put action are embedded close, and then a completely different projection, a completely different embedding space that looks at the video and at the nouns, right? So this is a verb embedding and a noun embedding. These can later be grouped to achieve the typical action retrieval, right? So you can look at the video embedding or the visual representation in both spaces. You can concatenate these and have an action embedding space, and similarly for the text, right? So we have a regularizing space that gives you actions, but we have these two projections, two viewpoints onto the space from the part of speech. So this is the model. Again, it's the same feature representation of the video, but it's two different projections of the video representation, and these are from the two different projections of the text. What this gives us is really interesting. We're looking here at the maximum activation example. So we have a neuron in the noun embedding space, and we're looking at which videos activate that neuron the most. You'll see more examples in the paper. But you'll see that you have examples of the chopping board in different actions being embedded close by in this noun space. So the action is ignored and the noun is set. And in the verb space, you have lots of videos of people doing opening and closing of actions. I'm going to show these again, just the verbs. So these are open and close of different objects, right? So in that space, there's one neuron that activates all these open/close. And it's interesting that it prefers to combine open and close together into one neuron. Right, this is really achieving a good, decent understanding compared to all other approaches to look at the text, right? So all of these are single embedding spaces that can take the verbs, the nouns, the full caption, any combination. And this is this representation that has these projections before they being combined. And regardless of whether you look at video to text or text to video, and we have these two splits of seen kitchens and unseen kitchens, you're achieving significantly, consistently an improvement. It also does a good job if you're doing zero-shot learning, right? Because you've learned the verb independent of the noun, so you can look at new combinations that you might not have seen. So this is a zero-shot example of zero-shot verbs, zero-shot nouns. We also analyzed these parts of speech for Epic Kitchens, as well as another data set commonly used for action retrieval called MSR-VTT, looking at the part of speech and how they represent things. Epic is very much a verb-noun oriented, but other data sets have other things like adjectives or determiners. And we've shown that also for MSR-VTT, this multi-part of speech projections is consistently achieving performance. Right, and I suggest you can look at the paper for more details. I'm not going to overload you with the numbers, but it's doing a good job both for video to text and text to video. So this is the first bit that I'm going to tell you about how language can achieve compositional understanding. And in this case, we focused at different embeddings for different parts of speech. A more recent work that we presented in CVPR focuses solely on adverbs. Oh, I have a typo here. Adverbs. Focuses solely on adverbs. And it's called Action Modifiers, Learning from Adverbs. In this case, we're using standard off-the-shelf instructional videos because Epic Kitchen doesn't have these adverb projections. We just ask people to state something like, I am opening the cupboard. But in these instructional videos, you find longer sentences. You also find people tending to say adverbs when they're meaningful, like you need to turn the ball slowly in this particular task, or you need to make sure that this dissolves completely. So we are looking at the sentences that come with these instructional videos from YouTube. This is the How to 1 Million dataset, How to 100 Million dataset. And what we're doing here is parsing these sentences for verbs and associated nouns. And as I've shown you here, these parsers will tell you which verb does the adverb apply to. So how do we do that? How do we learn from these adverbs? And these are giving you a particular projection again of types of compositional understanding of the action purely from how you would do it. So we would have the video. We also have this parsed sentence that gives us the verb, the action, and the adverb, which we call a modifier. You'll see why that's why the term M. So what we attempt to do, again, this is an embedding space. We're trying to project the video close to the modified verb. So if green is the embedding of the verb roll, we want to learn this modification, which is a transformation in the embedding space that makes rolling happen quickly, right? So as a result, you want to embed the video of rolling quickly close to this modified action. This is the same as undoing the video, right? So you can apply the reverse of this transformation and ensure that rolling is no longer being done quickly. So this is a revertible transformation, but in this case, we're applying the modification to the action, and then we're embedding the video close to this modified action. And things would have been quite difficult to start with to do this task, but this has been added by the complexity that these videos are not really very well aligned. People are saying, and now you roll quickly, but that might not be exactly positioned at the moment rolling is taking place. So in this work, we're learning this in a weekly supervised manner. And as a result, we're looking at the video around this sentence. We'll have different clips. Then these clips will be extracted with features, but we are looking to find the position where the person is rolling something. And thus we are using the transformer, and the query for that transformer comes from the action. So the action is being used as the query in the transformer to find where in the video rolling happens, and then where that is, this is where it's being embedded close to rolling quickly. And this is trained jointly. The features are pre-extracted, but the attention as well as the embedding space is learned jointly. Now let's see some examples of the result. What you'll see is a video. We know the verb we're after. We know that there is a mix. We don't know the adverb. And so you'll see the thickness of the border is indicating the attention, right? It's when is the mixing happening? And then at the end, after this attention is incorporated, it's predicting the adverb. So remember, it knows here what the verb is. It's trying to actually focus on learning the adverb. And it assumes that adverb applies to a variety of seen as well as unseen actions. So this is again another mixing action, and again seeing the video, and it's observing the bit in the video that's relevant and then predicting the adverb. And I'll show you a few examples. I like the turning action, yeah, so that's the person is turning, and again it's looking at the video trying to find when the turning happens, and then when it happens, that's when it's predicting the action. We're currently learning it for 6 adverbs, so it's not huge, but this is the first work to look at adverbs for basically learning from adverbs to learn how actions take place. Right. So until now, I told you about how can we use language to give us these compositional understanding. The first was giving you these projections into the space of action and objects. And the second is trying to give you this understanding of how you're performing the action from adverbs. And I'll lose at the second bit, which is actually motion. I'm just monitoring time. Okay, we're fine. How can motion achieve compositional understanding? Can I use motion to give me an understanding of this compositionality? And this is the work we again presented in CVPR. And we'll start with Epic Kitchens here. And we have a 2-stream action recognition with late fusion. So you have appearance, you have some 3D convolutions that predict from RGB. Then you have the optical flow. And again, you have an i3D that's projecting flow. And then you're doing late fusion to classify the action. If you actually learn this from all the actions observed in one of the kitchens of Epic Kitchen, then you try to predict these actions from a completely different kitchen. This is the inference. You'll realize it does really badly because it had only learned from a single environment. Worse, if you look at the space, the feature space you'll realize that the feature space is completely separate between these two kitchens, right? So where the source is, which is kitchen 1, and the target, these don't overlap. This is a known problem. This is a domain gap, right? Because you're learning in a different environment. How would you do that? You can do that by starting to label a graph of what the action looks like and try to map that into another space. But you can use modalities again here to give you this generalization. Let's see how. Let's try to use the knowledge that the motion might be more transferable to a new environment, but more significantly, let's use the correspondence problem as a self-supervised auxiliary task to perform this. What is this doing? It's just looking at the input, at the two modalities, and seeing whether they come from the same action, whether they come from different actions. So if the appearance and the motion come from the same action, then this classifier is giving you one binary class. If it's coming from a different action, so sampled, it's a correspondence problem, then it's giving you 0, basically, 1 or 0. It's purely a binary correspondence task. But because this doesn't need labels, this can be applied to both source, i.e. kitchen 1, and target, kitchen 2. So here we're assuming we have access to the footage of the second kitchen, but without labels. So this is an unsupervised domain adaptation problem. Once you apply this self-supervised task, you will see that the space of target is now clustering into these action clusters because it's learning the correspondence between the appearance and the motion. So it's no longer this stretch of red space that is unrecognizable. It's doing this clustering. It's still not very well aligned with source, but it is kind of achieving this a better understanding of actions in the new space. To achieve alignment, then we rely on the non-adversarial solution. So we say you now no longer should be able to distinguish where the footage is coming from, and this is being done by gradient reversal layer. So you kind of remove any information that allow this adversarial classifier, this domain classifier. And you do the same for the other modality. So you have a domain classifier for RGB and a domain classifier for flow. This combination achieves now this overlap. So if you look at two, in this case, cutting actions, you as a human can easily know that it's a cutting action. And you say, oh, there is a lot there. There is a chopping board. There is the oven. The system should be able to do that. But if it's relying purely on appearance, it really can't bridge what you have in your brain. You'll see that the source-only performance, these two videos are very far in space. Purely by the self-supervision auxiliary, they're getting closer. But more importantly, as we said, the target is getting these clusters. And along with this adversarial, that's when it's achieving this perfect overlap and classifying the target, which is the unseen video, not the one you've used to align, correctly. These are some of the results. So if you use source only, that's the performance you get. Purely by the self-supervised task, you're achieving better alignment and thus improved performance. Purely by the adversarial, you're achieving good performance, actually better than self-supervised alone. But their combination consistently outperforms. And what you see here is a mean across 6 different experiments between different kitchens. Right, we can look at the paper for more details. But this is an attempt we've done at using motion to achieve this compositional understanding and thus generalizability to new actions. Right, there is another work that we've done. It might not look very obvious how you can use it to achieve compositionality, but with a bit of a stretch, I hope you can see the intention. So we're going to look at the video and I'll ask you to label that video. What action do you think is observed in this video? And I hope some of you will come up with an understanding that this is a closing of a box or a closing of a Tupperware. The trick is, this video was never captured. This action never happened. This is the action that has actually taken place. And what we've been looking at is a time reversed version of this action. Let's see that again, because kind of people tell me, oh, you have fooled us. So let's see the action again. It's a very valid action of a closing action. And it's actually a time reversed version of opening. This is interesting because until now in computer vision, this arrow of time has been perceived as this thing that once you go in the reverse direction, then things break and things don't work, and it has been used as evidence to train models or to pre-train models. In this setup where we're working as a group in this object interaction, this is not true. There are reversible actions. You can close something and open it again, and close it and open it again. The world in this case is reversible. Reversal is not the same as the waterfall that you see when you talk about the arrow of time, right? That water doesn't come up. So in the subset of work that we talk about, which is object interactions, and as you see from the line of work, this is everything that we do in this group, then there are reversible actions. There are actions that when you reverse, they don't change label. They are additional, valid data augmentation examples. And in this work, we also ran a user study by giving people reverse time and forward time and showing that people prefer them with equal chance as examples of the class. There is also this equivariant classes. So videos that when you reverse, they are valid examples of a completely different class. And interestingly, this is an equivariant relationship. That means if you have videos of that class and you revert them, you're back to class A. So it's A to B, B to A. And of course, there are irreversible actions that break the rule of physics. We're not denying their existence, they do exist, but there hadn't been a prior work to look at the second aspect, the equivariant ones. Also in this work, we use this to achieve zero-shot learning. By that means I'm showing you a confusion matrix of aspects of this something data set. And every other class in this subset is zero-shot learn. What does that mean? So let's look at this class, burying something in something, and its corresponding one, which is digging something out. We've taken the burying action, we've trained it for burying, we reversed those videos, and then we've trained them for this digging out. In testing, we have valid forward time digging out action, right? That's why it's zero shot. So we've never seen digging out, we've just seen the time reversed version of it out of burying. And the diagonal is pretty promising. The fact that we can still recognize all of these, as I told you, every other class here is zero shot. If you want to look at this work, it's called retro actions. And the videos around it are really interesting to look at. Again, we are in this subset where object interactions take place, and we're showing that time can be reversed into valid examples to train models. Right, so here we're using maybe, let's say, combination of motion and language, but we're able to kind of achieve this understanding of the objective or the outcome of actions and how they can be reversed. In the last part of the talk, I'll tell you a little bit about audio and how audio can be used to achieve this compositional understanding. And again, we're looking at the space of object interactions, and we'll show you an example here. I don't have a video, but you can imagine what we were talking about, of someone breaking an egg. Right, so let's look at the task of breaking an egg, cracking an egg, and what you would do. You would first tap the egg, and after that, you would actually open the shell, and only towards the end, you will see the visual appearance of the change of the egg appearing out of the shell. Interestingly, the discriminative nature of these three modalities occur at very different times, right? So the sound of cracking an egg is not at the same exact location as the motion, and the motion is not at the same exact location as the best visual appearance. So we started this work trying to think, how can we merge these discriminative notions? We stumbled upon, well, searched for an aspect of this that's very well understood in experimental psychology called temporal binding. And the experiment that psychologists do is as follows. They would show you a video of a plate breaking, and you would hear the sound of the breakage. They would then shift the sound into an incorrect position, right? They would move the sound. It's still close to the video, but it's not correct. It's not really synced with the visual you're seeing. And humans are very convinced, and they will report consistently that they believe it's in sync. So the mind is binding these modalities even if they are out of sync. There are lots of theories about the reason why people do that. You can say the speed of sound and the speed of light. However, the shift is much bigger than the difference between the speed of sound and the speed of light. Interestingly, consistently, there is evidence that children have a bigger temporal binding window than adults. So this is something that you learn as you grow, right? It's not something that's embedded or fixed. So we thought, okay, if children are learning with a big temporal binding window, then neural networks should, right? Because our assumption is neural networks are infants, so they have to be as as good of, if not more naive than children. So in this work, we built this network that actually attempts to do binding within a temporal window, but also progress over time in a style. In this case, it's a TSN style, so it's sampling windows, but within this window, it's merging modalities that are out of sync within this temporal binding network width. So each window is sampling an audio, a visual, and a motion, not exactly in sync, and then concatenating and doing a naive late fusion. In the paper, we also looked at more interesting fusion approaches, and they didn't prove to be significant. The outcome of this model is the two outcomes of Epic Kitchen. So these are the verb classes and the noun classes separately. We always train Epic like this, and it seems to be kind of doing the best thing for us. So it's a two-head output. Right. And if we look at what audio is giving us here, it's also interesting to look at what it does. So which exact confusion gets decreased? So anything that is in the negative, that is good if it's off diagonal, right? So it's actually decreasing the confusion of the diagonal and increasing the confidence on the diagonal, right? So you have examples in the paper about these confusion matrices with the addition of audio in particular. Also, if you look at the individual classes, you'll see that certain classes achieve best performance by one of these different modalities. And you can think of this purely as a compositional understanding of the types of actions that we might have, right? So there are actions that are purely RGB focused, there are actions that are motion focused, and there are actions that are audio focused, like spraying or turning something on or off, right? That kind of, this is an egocentric data set, so camera is wearable. That means actions like eating, you only hear them in the audio, you don't see them, right? Because the person is chewing while wearing the camera. And it's the same case for nouns. You can look at what type of modalities achieve better performance for nouns. Of course, very rarely do nouns get better performance by flow unless they are tools like knives and spoons, right? That's when purely their motion is what matters to them. But you have lots of visual understanding. You also have lots of audio purely because they have an actual audio like the extractor fan, or they have material things like the foil or the napkin. I always get asked about blueberry and grape and why they end up under audio, and it's because of the packaging. They tend to have like these very unique packaging, so they get clustered. And you can see also the examples that get classified by all these modalities jointly, equally importantly, like the microwave. It equally importantly has a distinct appearance, a distinct flow motion of how you use it, and a distinct sound. Let's see some examples, and we'll go through the video. You're going to see the ground truth, how RGB is predicting purely RGB, purely flow, purely audio, but more critically, this temporal binding approach that's looking for out of sync modality matchings. This example in particular, I always like it because if you close your eyes, you as a human can confidently know that the person is peeling onions. Like, it's very audio driven. Oops, sorry. Oops. And I'm not saying audio solves it all, but the interesting things about the egocentric type of data collection is that the camera and the audio are moving with you and are as close as possible to the action. So actions like drying, you think, is there anything there? Yeah, there is. There is enough in the audio signature to pick things like drying or opening the drawer, not only closing it, because of the close proximity of the microphone that's traveling with the wearer close to the action. And you look in the paper at things where we show that audio generalizes better into new environments at times. But of course, there are also, because it's in the kitchen environment, you have very typical materials. right? So the sound of cutlery or the sound of cookery, like it's the same even if it doesn't look the same to you. And we also show how the TBN is very good in dealing with some irrelevant sounds like music playing in the background. Of course, there are also silent sounds that it might not pick up. But this TBN approach achieves the best performance because it kind of selects which modality to learn from. And as part of Epic Kitchens 100, sorry, it's like a full thing that I got out of the paper, just to show you that what TBN does compared to other state-of-the-art action recognition, even though currently on top one action, TBN is not the top performing, when it comes to tail classes, it's outperforming things like slow fast or temporal shift network, temporal shift module, because of its ability to kind of leverage the audio aspect of the approach. And increasingly, people are recognizing Epic Kitchens as a data set that's really good for audiovisual understanding because of the rich audios in kitchen environments. Before working on Epic Kitchens, I thought I'm not gonna work at all in audio. I thought I'm a vision person, I'm not doing audio, until we started annotating Epic Kitchens. And one of the students came back and told me, if we enable audio, we will get more accurate annotations. And I thought, okay, that's the most ridiculous thing. I thought not to introduce audio. If annotators are going to achieve better performance, then the system and the methods that we're going to use should have access to lots of audio. And many of the approaches you've seen that I presented before, like the action retrieval, we're using features that come out of TBN, so they have access to the audio of the action. If you want to look at Epic Kitchens 100, I also advise you to look at the model that we already have pre-trained on TBN. So you can already get like a decent performing code and pre-trained model on this large scale data set. Right, so in this work, I tried to answer the question of how can multimodality achieve compositional understanding, looking at audiovisual, language, and motion. I get the pleasure of coming and presenting all these aspects, but this is the effort of a small but very effective and caring team that I'm very privileged to work with. Collecting a data set as big as Epic Kitchens for a group as really as small as us was a big feat, and we're grateful to the community for having picked up the data set as an interesting one. And if you have any questions on the data set, don't hesitate to email us as well. We keep the email address very actively monitored to assist people as they use the data set. And in the interest of time, I am exactly on time for the Q&A session.
Thank you so much, Dima. That was a great talk. If the audience members have any questions, please feel free to type it in the QA feature. It should be in your bottom right of your Zoom window. But in the meantime, I had a couple of questions that I wanted to ask myself. You made a comment during the last paper you were discussing about how audio generalizes better to new actions. Could you say more about that?
Right. So we have lots of things in Epic Kitchen that you might have an object that looks very, very different in a new environment, like a particular bowl or a particular pot, right? And if you might not be able to recognize what it is. We also have different lighting conditions and sometimes not very well lit environments. And that's where audio is perfect. But I think in the kitchen environment, there are things that are generalizing perfectly, like the sound of water. If you open the tap, right? I see that almost in every case, even if you've never seen that particular kitchen or that particular tap, the sound of opening and closing the tap kind of is perfect. That's why I say particularly in environments like the kitchen, where material is very consistent, whether it is water or the sound of frying or the sound of the kettle or the actual sound of cupboards and fridges, right? Even if you haven't seen that fridge before or it doesn't look at all from the outside like a fridge, the sound is very consistent. So at least in this domain, audio is definitely better than RGB to generalize to an unseen environment, and at times outperforms motion.
Thank you. The other question I had was around the paper where you were learning adverbs. And I was wondering if you could, maybe elaborate on whether you thought about transformations that you could make on videos by modifying the adverbs that are being used to describe the kind of actions that are happening. So for example, you had a case where someone was mixing something quickly. Have you done work in terms of transforming that video where now someone is doing it slowly instead?
Yeah. So it is a very interesting question, and you would think, as an outcome of this transformation, that you would then find that going exactly in the other direction with exactly the same distance will take you to the best possible learned position of slowly, right? That's what you would think it would do, but it doesn't, right? The visual representation of how something is being happened quickly in this space is not the exact opposite of doing it slowly. To do the best transformation, and we've tried that, you can undo quickly and do slowly. You can do that, but it's not really, it's the best transformation of quickly is not really any opposite direction. If you try to enforce that, the performance is worse. You might think of quickly and slowly as one example, but think of other things like chopping something finely versus coarsely, which is another example, right? These are actually in the same direction, but with different extents. Again, if you think one of them is like, I would expect that one to be a small step in the same direction as the other, and you try to enforce that representation, the performance is worse. It's really not doing that. It's learning its own independent representation. So the regularization we have here was related to generalizability to a new action. So expected it is the same modification across actions. Perhaps if we didn't do that, it will result in something different. So we wanted quickly to generalize to all different action representations. And you have to think, this is a hard task. Like rolling quickly is different than mixing quickly, is different than picking up something quickly, right? So that's what we wanted to generalize to. If we were not interested in that and we were optimizing locally within one action, we might have produced something closer to what you're after. So it depends what you want. However, as I said, we were able to undo one and redo another one, right? So coming back to the action and then going from the action to another class. But that's not exactly so you can undo the adverb and apply another one, but it's not tying them tightly as antonyms of one another.
Great, thank you so much. That's very fascinating. Yeah, it seems like there's a lot of interesting work that could take these ideas and move it forward quite a bit in future work. So that's great. It seems like there's a lot of new avenues to explore here. Okay, I think those were my questions. I think there's an audience question as well. Let me see if I can pull it up. Yes, so this is an audience question. Great work. Have you done studies to make sure the model is not learning spurious correlations in the data set?
Is it Epic Kitchens or?
If the person asking can clarify.
In general, if we want. So for Epic Kitchens, we have lots of things that, we have lots of things that are trying to kind of achieve some element of generalization. So as I said, we have these unseen kitchens. So we have participants that have not been seen at all before, for which you test the performance. We have the performance on your tail classes as well as your head classes. However, it's very difficult in Epic Kitchen to look across datasets because there isn't any other egocentric dataset that we can actually work on. Like egocentric footage isn't lying around in YouTube as yet, right? The notion that you give someone a camera to wear on their head or to wear on their glasses, which we hope is the future, is not yet there to test on. However, we're consistently impressed by what people are doing with the dataset and how they're applying it to new problems. We also have this notion of, does it generalize to other people, to other maybe cultures and other things? So there are correlations in the dataset that we can't claim we can generalize to. I was asked when I presented some of this work in India, whether this will work in an Indian kitchen with the amount of tools that they have, and I presume not. So of course, this is within what it had been learning, but we've tried different things. We collected the data in 3 countries. The narrations are produced in 5 different languages, and we were testing on unseen environments by different participants. Maybe the right answer is this is very much open to the community to test whether there are correlations in the data set that we might have missed, but we're producing the platform to allow people to explore that, especially with these different challenges that we have. So we have a retrieval challenge that allows you to look at captions labeled by someone else in an unseen environment. So both the caption and the sentence are new. And we also this unsupervised domain adaptation where you've seen footage with no captions. But again, I think like any data set, there will be some biases. It's impossible to assume. For example, data sets that are collected from YouTube are biased towards these things we need to learn, like these how-to stuff. So these exist. Perhaps the biggest bias I believe the data set has is the fact that it's collected in what I would say Western countries, making it completely not suitable to generalize to environments outside the data it had been collected within, if that answers your question. But if there's a particular aspect of it you want to ask, I think, as I said, we didn't give any instructions to individuals as they collect. And we relied on what they told us the actions are to label. So it was narrated led as opposed to a list of actions we wanted to label.
Great. Any last questions from the audience?
In the meantime, I have a question. Maybe it's a topic we've discussed before on the high level. I wonder your thoughts on epic kitchens for long-term event understanding. I think a lot of these benchmarks you have shown so far really focus on the short-term understanding, but clearly, I think we agree that long-term is quite important. So, do you have anything in the future coming up, or any thoughts on how to get there through your?
Yes. So we're working a lot on that. So the difficulty in long-term understanding in natural setup is that humans are not robots. They do things in very complex ways, as in you would leave something burning, like not burning, on the oven, and then you would go to wash the dishes, and then you would come back. And so people are very, very, even action anticipation on epic kitchens is really difficult at times. Perhaps the best thing that I believe is very interesting that people haven't done yet, including us on epic kitchens, is that we've released the footage with the time of day they were captured, and they are across 3 different days. And I'm yet to see any work that had looked at, let's say, morning routine across the days. It's out there, the data's out there with the time of day and with whether you return to the kitchen after 10 minutes. They are different videos, they're called video 1 and video 2, but you see the temporal gap between them. And I've done old work on routine modeling, and when we collected the data set, that was one of the aspects. Currently, this is not an active area of research we're working on, but kind of I keep talking about this and I'm waiting for someone to pick it up, because there is a lot to do with the time of day understanding and the routine understanding within the data set. And now with this 2 years on, it's even more interesting, because you've seen, you can even look at the change in routine of behavior of someone 2 years later. And it's the same individual in the same kitchen. And you see, by looking at the videos ourselves, we see some people becoming healthier after 2 years or becoming less healthy. Maybe it's waves, right? We all go through these waves of becoming healthier or less healthy in our food. So I think there is a lot in the data set that we can add. And now Epic Kitchen is spurring bigger collaboration. So there is now a big collaboration that is being spurred by Kristen Gruman and others. So there are 11 universities collecting, not exactly Epic Kitchens, but let's say more egocentric footage, very much unstructured and very much with giving participants no instructions to collect interesting scenarios. So Hopefully we're moving out of the kitchen at least. However, I still think the kitchen is the hardest environment. If we solve the kitchen, I would guess most of the other scenarios would be quite easy to resolve. Some of the participants in this big consortium are collecting some occupational work. So that might be harder, like if you're working in a workshop or building constructions, etc. I think long-term is a big piece of interest, but the problems are not yet very well defined. We need to think about those problems that are properly well defined. We can test them, we can evaluate them. And in my head, predicting next day's routine is something that Epic Kitchen can do. And maybe when we talk next time, that paper would be out.
That's excellent to hear. Thank you. I think there's one more question from the audience.
Shall I read that question about the slide on Epic Fusion? Can you elaborate why where relies on audio? Right. And similarly, throw relies on RGB, not flow. Okay. What are the insights that the model can leverage with different modalities? Prior work has shown that the model is more biased to use the text modality. There is no text modality in this one though, right? So text here is the output. The three modalities we're after are RGB, flow, and audio. So, but I think you're talking about the typical biases, right? I can tell you why where again is the same as eat. So we're talking here about the person wearing the apron, right? And again, the sound that you're gonna hear is purely in the audio. You're not seeing that action of wearing because it's self-wearing, right? Someone is kind of putting the apron on, but you can see the tie, you can hear the tying very clearly. So again, eat and wear is a bias of, well, not a bias, it's an outcome of the data set being wearable. Why is throw more sensitive to, where are we? To RGB than to flow? I think it's because there are very, very different notions. So it is kind of preferring the location of the bin, the visual presence of the bin to identify throw than the motion. So in this case, it's a more, throw is usually when you kind of dispose of something, and that typically is very positioned close to where the bin exists in the data set. And that's why it's a more discriminative pattern for this particular action as opposed to something falling or putting something down. At least that's my understanding. I'm not very confident about throw. Maybe if you want to drop Vangelis an email, he can tell you more, but I know that where is something we've discussed, and it's very much what you can hear as people tie the tie. Prior work has shown that the models are biased towards the text modality. The text here in this case is participant driven, but there is a bias in it. And I can tell you one bias that we've noticed in the first version, which we tried to resolve in the second version of the dataset. So we asked people to say what they had done in the video, and they were more likely to label the opening of the cupboard than closing it. Their brain would have moved to the next goal, and they would kind of miss that action altogether. So, so there was a particular bias in the narration, the text modality, that when you ask people to say what they've done, they will focus on what we call goal-oriented actions and miss other actions that might exist in the video. You can see them, but their brain just dismisses them. So this is a selection in the narration. And that's why we introduced in the more later version something called pause and narrate. So you have to stop with the action, so you can't miss actions. And we observed an increase in these actions, so they're missed less. They're not completely 100% there, but they're missed less. And that's what allowed us to now introduce an action detection task, which we couldn't in the first version, because there were some missed actions in the data set. I hope that answers your question. I tend to be very disciplined. If someone tells me that the slides need to be 45 minutes, I always finish in 45 minutes. That tends to be not what academics do. The typical academic performance is to always say, I have more slides than time provides. But I find that more disciplined. So if you're interested in understanding more about the work, then please refer to the papers.
Thank you so
Thank you,
much.
Dima. I appreciate your discipline.